by showing you a video, and hopefully you can hear the video. If not, I'll make sure the sound is working. I'll show it again. It's a very short clip, but hopefully it will work and it's not buffering too much for you guys. I think with everybody, all these teachers now on Teams, I think things are buffering and
Safa Paul ist der schnellste aus den Blöcken jetzt.
Set.
Safa Paul ist der schnellste aus den Blöcken. Jetzt kommt Gay und jetzt ist Usain Bolt nicht zu halten. Nein, er gewinnt. 0,58 Weltrekord. Ein Wahnsinn.
Set.
Safa Paul ist der schnellste aus den Blöcken. Jetzt kommt Gay und jetzt ist Usain Bolt nicht zu halten. Nein, er gewinnt. 9,58 Weltrekord. Ein Wahnsinn. Da denkst du dir...
now, has anybody ever seen that race before?
Yep.
That was the 100-meter dash, Usain Bolt, who set the record for the 100-meter dash, the fastest recorded time ever. And that was in the Berlin Olympics, I believe in 2009. I don't know why I want to say that. But it was quite the race. I remember watching that live. It was a very hyped up race there, and unbelievable how fast he was going. We're going to get to that race in a second. But here's what I would expect for you to know so far. And actually, I'll come back to this, okay? We're going to go right to 5.4 here, okay? So Usain Bolt of Jamaica set the men's world record in the 100-meter dash. He ran 100 meters in 9.58 seconds. Now, I don't know if you can remember being in my classroom, but the width of my classroom, okay, from one wall all the way across to the other wall, not from the smartboard to the windows, but from wall to wall is 8 meters. So add 2 more meters onto that, and Usain Bolt was running 2 more meters, 10 total, in 1 second. That's how fast he was going. It's incredible. As a rate of change, here's what was happening with Usain Bolt. His speed was actually equal to distance over time. The amount of went 100 meters in the time 9.58 seconds. When we calculated this, 100 divided by 9.58, this is a rate of change. Rise over run. His rise was represented with his distance. His run was represented with his time. And if you can picture that on a distance time graph, on the bottom was time and on the side was distance. It's almost like that CBR. And he went 100 meters in 9.58 seconds. If we were to keep going and actually divide 100 by 9.58, how fast was he going in 1 second? That's actually what we're doing when we divide. And when we figure that out, that question mark is 10.4 meters per second. That's over the length of my classroom in 1 second. It's incredible. Fastest recorded time ever, so 10.4 meters, and that's not even, that's his average speed. I mean, right at the very beginning, he had to get up to his top speed, so his top speed might have been more like 12 meters per second. Pretty incredible. So you can write that in on your handout. And then underneath it basically says that this means Usain Bolt covered on average 10.4 meters every second. This is an example of a rate of change. If I were to ask you how fast Usain Bolt was going, you would say 10.4 meters a second. If I were to ask you for his slope, it would be 100 over 9.58. This is more of a slope, rise and run, and this kind of translates into something a little more meaningful to us, which is 10.4 meters per second. That's his rate of change. Slope and rate of change are the exact same. It's just the context of which is better in that certain instance, okay? So how do we find the rate of change from a graph? Well, let's take a look at this graph at the bottom. You have all these different animals and people here and how fast or how far they can go in 10 seconds. It's always 10 seconds for each of them. So it's almost like we have this dotted line at 10 seconds right here, and we see how far they can go. So first of all, the Olympic sprinter, Usain Bolt, on average in 10 seconds, he can go 102 meters. That's the average, okay, sprinter, not the world's fastest, but pretty close. Believe it or not, if you lined up a polar bear onto the 100-meter dash line and had a race, the polar bear would beat Usain Bolt. So never try to outrun a polar bear is what they say. A polar bear is faster than an Olympic sprinter. This blows me away. I've never ever understood this, but an alligator actually is faster than a polar bear or an Olympic sprinter. Think about how fast Usain Bolt's going. An alligator is 1.5 times faster. Now alligators can't turn too well, but straight away they can move. And I watched a video. I tried to find it, but I couldn't. But they can go very, very quick. So that's pretty scary to know an alligator can go that quick. 150 meters in 10 seconds. An alligator will win the 100-meter dash. A cyclist can go 165 meters in 10 seconds. Then we get to the fastest land animal, which is a cheetah. Okay, and I'll show you a quick video here about a cheetah, and I think you'll like this video here. Can you guys hear the volume okay?
No!
Who was that?
Me.
Who's me?
Michael.
Yeah, you don't have to be so rude, Mike. You can just say no.
Sorry, my sister's cooking up eggs. Like, actually, though.
As soon as this starts here, sorry about this. I think it's because everybody's online again.
Tropicana orange juice provides 100% of your daily vitamin C.
Before testing our recruits, let's try a virtual matchup between a cheetah and the fastest recorded man on Earth, Usain Bolt. In 2009, Usain Bolt set a world record, meters in 9.58 seconds. That's blazing fast, nearly 28 miles per hour. A cheetah's top speed can reach nearly 70 miles per hour. Let's put a cheetah on the track for the same event. This gives a whole new meaning to the term fierce competition. The cheetah takes off and is quickly ahead of the entire pack of human runners. In just 5.95 seconds, the cheetah has won, beating Bolt's record by more than 3.5 seconds. Not even the most gifted sprinter can match her. What if we give our human runner a head start? How much would we have to hold back the cheetah to make a more even race out of it? Let's hold the cheetah in the starting block and spot Bolt as much as 40 meters out of 100. That would leave only 60 meters left to race.
Set.
We release the cheetah. With amazing acceleration, she catches up, and they cross the line at the exact same time. What's her secret? First, a cheetah is packed with more fast-twitch muscles. muscle fibers built for quick bursts of power. Humans have more slow twitch muscle fibers, which allow for greater endurance but are less effective in a sprint. There's her spine, which, like an archer's bow, springs her forward the maximum distance with each stride. Once she's off and running, she's halfway to Bolt's position in just 1 second. Bolt is slowing down while she's literally going airborne with each 7-meter stride and gaining speed as she goes. No wonder the cheetah wins in about half the time.
So what's pretty incredible there is when they hold back that cheetah, and as soon as they release that cheetah, they said the cheetah is cutting Bolt's distance in half in 1 second. That's incredible. So when we go through all of these animals and people, here's what we can say. Let's start with an Olympian down at the bottom. So the speed of an Olympian. We did this with Bolt up top, but average 102 in 10 seconds, and that's 10.2 meters per second. So that's how fast an average Olympic sprinter would be going, okay? When we go with the polar bear, so the speed of the polar bear is also distance over time, 111 over 10, and dividing by 10 is pretty easy. You're just moving the decimal twice. I got 11.1 meters per second. So notice this polar bear can go an extra meter a second, okay, much quicker. An alligator, 155 over 10. A cyclist, 165 over 10. And then we get to the cheetah, which is 311 over 10. So notice the difference with the cheetah, 31 meters per second as opposed to 10. It almost looks like in the short term, 3 times as fast. Pretty incredible. So I'll give you a second to copy these out onto your page. We just determined the slope of each one. So this is slope, and this is what I'm hoping you get out of it. This is your slope, rise over your run. But when we talk about rates of change, this is more of a rate of change. Okay, the units are there. And they're the exact same, okay, given the context. Slope, rate of change. If you haven't already done so too, in the comment section, please just click on the link. That's how I'm doing attendance today. And just tell me what cohort you're in, and I'll be able to do my attendance afterwards. So please just make sure that you've done that. All right, just let me know when you guys are done. Again, I am recording this, so if you need to go back just to fill in some stuff, you will see this online once I'm done. All right, are we good to go?
Yep.
Anybody else want to pipe in, just so I know? There's a few of you.
Yeah, we're good.
All good? Okay, perfect. Again, if you need to copy out, you can see how it's done. It's just the second number divided by the first, okay? Just by curiosity, you see all these blue lines here and what's labeled. Does anybody know what animal this red would be? You may have seen it on the YouTube. There was a link up top. Some of you may have saw the link.
if we're talking about fastest fish, then it would be the sailfish, but fastest bird, it would be a peregrine falcon.
That's correct. So, what were you saying about the fastest fish?
Sailfish.
Sailfish is for sure. I wanted to make sure I heard it right, but I think the absolute fastest animal in the world is the peregrine falcon. I do have a video which is pretty cool. This is the last one here. Hopefully it works right away.
When I Googled the fastest animal, this is what I got. A cheetah. A cheetah. A little mammal bias, maybe. The truly fastest animal on Earth has a max speed 3 times greater than the cheetah. Peregrine falcons can leisurely cruise through the skies between 40 and 60 miles per hour, but when they're diving toward their prey, they can reach speeds over 200 miles per hour. That comes out to 293 feet per second. It's like flying the length of a football field in 1.2 seconds, or the length of this DC block. So how is it even possible for peregrines to dive this fast? A peregrine falcon is around the size of a crow, weighing between 1 and 3 pounds with a wingspan up to 3.6 feet. They prey on other birds by dive bombing them and snatching them midair. The first thing you see when a peregrine goes into its dive, also called a stoop, is their bullet-shaped body. Notice how the peregrine tucks in its feet and sweeps back its tail and wings. This streamlined figure reduces wind turbulence, maximizes maneuverability, lift, and speed as it cuts through the air. It wouldn't be able to do this nearly as efficiently if it had broad wings, like a hawk or an owl. But the peregrine's wings are pointed and angled back. And because of its stiff, unslotted feathers, it experiences less drag. The wind would pull on loose feathers on other birds. Peregrines also have a large keel, that's this breastbone. A bigger keel supports stronger chest muscles. Acute vision allows them to spot prey a mile away. The nictitating membrane, or third eyelid, helps to maintain their vision in their high-speed dives. And the secretory gland keeps their corneas from drying out because of all that wind. But none of this would be possible if the peregrine couldn't breathe. The air falcons experience while diving would make it impossible for most animals to breathe. But they have a bone in their nostrils to slow down the airflow. They also have robust hearts that beat around 600 to 900 beats per minute. All birds have a vastly more efficient respiratory system than mammals. Then, prey, the peregrine is pulling around 25 Gs coming out of a stoop. Compare that to an F-16 fighter pilot who endures up to 9 Gs during some maneuvers. On speed alone, peregrines are formidable birds of prey, but it isn't their only adaptation of note. Footage from our friends at BBC Earth shows where this wanderer has made its mark in some unexpected places. After a sharp recovery from near extinction in North America, bustling cities with soaring skyscrapers and towering cathedrals have become mini peregrines' new kingdom. A plentiful hunting ground with high perches and deliciously plump pigeons.
All right, so you can see how fast a peregrine falcon would go in relation to a cheetah, much steeper line, okay? They were saying almost 3 times the speed of a cheetah, which is incredible. It's hard to wrap your mind around some of those numbers, just how fast things are moving. So let's move on to the back side of the page, and let's fill out a couple blanks and do a couple examples, and I'll get you working here today. So that being said, let's go over the key concept here. Key concepts. First of all, rates of change. So a rate of change is a change in one quantity relative to another. So you need 2 things working together or against each other. In the previous page, it was all about distance and time. That's a rate of change. Okay. Maybe it's the amount of hours and how much you get paid at your job. That's a rate of change. So many hours, so much money. Okay. Now, unlike a slope is a number over a number. That represents a slope, okay? Unlike a slope, a rate of change requires two things to be compared, and there's usually some units that go with it, meters per second, so on. So what we need are units such as kilometers per hour. We need some type of variable name with it. That's included in a rate of change. When a relation is graphed, the slope describes the rate of change, and that's the key. On the previous page, slope was in yellow. Slope was in the yellow. Come on. Slope was in the yellow, and the rate of change was in the green. That's what we saw on that previous page. Okay, so down here, slope, rate of change. There are the units. They're exactly the same. They're just a different context. It's like Mr. Bracken and Dave again. Mr. Bracken, Dave, same thing, but one's a slope, more of a number over a number, like raw numbers. This is more of what's the context of it. To find the slope of a line segment, just join 2 points, and you can subtract your y values to get your rise. And you can subtract your x values to get your run. And I'm going to go over this with you here, and I'll show you why it's important. Okay? But I'll let you copy that out. I'll wait for a couple people to pipe in that they've got it copied out, and then I'll move on here.
I got it copied.
I've got a copy.
Good, good. Everybody's good? Excellent.
I don't yet. Oh.
Oh, okay. No problem.
I'm good.
Okay, everybody's good? All right, so therefore, your slope, which is m, that's what m stands for, is slope. Okay, and I'll even clone this. I think it's worth it to put that here. I want to make sure you know that that m value means slope, okay? So whenever you see m in math as a variable, we know we're talking about slope or rate of change. So that m value, slope, we know is rise over run. But there's another way to show it with this triangle with a y over this triangle with an x. And this triangle is pronounced delta. It means change in. You will see this more and more as you go through high school in science classes when you're doing experiments. The change in the temperature, the change in the amount of material, the change in the bacteria, you'll see this triangle called delta, okay? So slope, which is m, is rise over run, or the change in y over the change in x. Now, I just want to show you something here. Don't copy this out, okay? Just watch here. I'll give you time to copy this out. When you take a look here, this is what we did yesterday. We started at our first point, wherever it was. And if I wanted to calculate the slope of this line, we went over 1, 2, 3, 4, and 5, and then we went up 1, 2. We ran 5, we rose 2, and the slope was rise over run. That's what we did. You can still do that. There's no problem with it, but I want to show you something else here, okay? This point A has the coordinates of 2 and then up 7. So I'm going to write this in on my graph right here for A, 2 and 7. Okay, you can do the same. So 2 and 7. And where I'm going to for B has the coordinates of always across on your X first, over to 7. That's my first number. And then I move up to 9. That's my second number. Now, using these points, you can also come up with what your rise and your run are, or your change in Y, your change in X. So take a look here. This is an X, this is a Y. This is an X, this is a Y. Every point is always in the form of an X, then a Y. So if I want the change in Y, I go to my second two numbers, the 7 and the 9. And do you see how I go from 7 up to 9? I've increased 2. I've gone from 7 to 9. So I can go over here and I can say, okay, the slope, M, of my line segment, and I write it down below as an AB, okay, is equal to, and I'll open up a fraction. I can now go, and I just got to find it here, there you are, change in Y over change in X. Another way to do it instead of rise over run. And when we go to our diagram, I say, okay, I start at 7 for my Y and I go up to 9. So my change in Y is a positive 2. And I look at my second numbers. I go from a 2 over to a 7. How much do I have to move across to get from 2 to 7? And that's 5. And we get the exact same numbers as if we drew in our triangle here. We just use the coordinates. Does that make sense? Is that okay with everyone? You guys try it to see if you come up, and if you can do this correct, try it with the following. You guys are going to do the slope of CD. And we are going to do, this is equal to, I'll open up a fraction, or a fraction, I guess, change in Y over the change in X. And what do you guys get as your number? See if you can figure that out on your own. I'll take it up in a second, and we'll see what we get here, okay? So what is the change? What are the coordinates of C? What are the coordinates of D? And then what's the change in Y? What's the change in X? And see if you get it. Coordinates of C are 4, 6. Over 4, up 6. The coordinates of over 9 and up 3. So when I take a look at my change in Y, I start at a height of 6. I end at a height of 3. I go from a height of 6 down to a height of 3. From 6 to 3. I lose 3. I'm not going from 7 up to 9. I'm going from 6 down to 3, minus 3. That makes sense to me. The line goes down to the right. All right, everyone, it goes down to the right. It should be negative. And again, I start at 4, and I go over to 9. I move across from 4 over to 9. I move across 5. And there is the slope of my line. All right, is everybody okay with that? Get a couple people chiming in, just making sure.
I don't understand how, like, the top one is negative, because if you go from, like, 6 to 9, like, it goes down, but then still if you go from 4 to...
Be careful. You said from 6 to 9, okay?
Oh, 4 to 9, sorry.
From 4 to 9,
yeah.
We move from 4 over to 9. That's a positive right there.
Yeah.
But we start at 6 and we go, let me go with green. We start at 6 and we go down to 3 for our Y, our change in Y. That's down 3. If we were doing this with rise and run, we would go down 3 from 6 to 3, and then we would go across 5, positive 5. Do you see how that works?
Yeah, I get it now.
But we don't have to mark up our diagram with these triangles if we've got the coordinates, okay? Now, is everybody okay with that part?
Mr.
Ayla
Bracken.
told me to let you know that her computer or her laptop just died.
It just died, eh? That's not good.
Yeah, she's getting back on. She's getting a charger.
Okay.
All right.
Mr. Bracken.
Yep.
Why is the -3 on top of the 5 instead of...
Yeah, so why is it negative here and positive here? When I go from A up to B, do you see how I'm going up from 7 to 9? I'm adding 2. I go from 7 up to 9. But from here, I start at 6 and I'm subtracting 3. I'm going down 3. to go from 6 down to 3. That's why there's a negative here. Okay. I look at this and I remember back in chapter 2 when we were doing scatter plots. This line goes up to the right. Guess what? It's positive. Do you see that? And take a look at this line. It goes down to the right. Take a look at that. Negative. Remember the basketball net and the number of shots I sink? It goes down to the right. That's a negative. Okay. So when I have a point C and I'm going to D, I notice I'm going down to the right. That means it's going to be a negative numerator, always a positive denominator. It's always going to be a positive denominator. Okay.
Okay, thank you.
All good? Now, some of you may look at this and say, okay, sir, that's great. We can use these points, but I find that a little more confusing than just drawing a triangle, going like that and figuring it out. Okay, some of you may say that. And I agree with you on a graph like this. But let's move to this next example and see why it's so important to understand this portion here using our points. The graph shows the volume of gasoline remaining in a car's tank. Now, you guys aren't driving yet, but when you do, this will become something that you need to keep an eye on, okay? So, just go like this. The first thing is calculate the slope of the graph. The problem that I see when I look over at this graph, distance in kilometers, the number of liters, okay, in liters, and I take a look at my line, I say, okay, this is fine. But notice this point. Do you see how it's not right between two lines and we may not know for sure what that is? That's an issue if you're not given the coordinates, if you're not given the points. So eventually this will blow up here. But this point is between 60 and 70. I just don't know how high that point is. Is it 64, 65, 66, 64.5? I don't know. And the same goes to this point. Do you see how it's between 0 and 10? But looking at these points, if I wasn't given these points, I wouldn't know what the coordinates were. But now I know, okay, this is 0 and 65. This is over 500 and up 5. So what's my rise? I have to go down from 65 down to 5. I've lost 60. That's the change in Y. From 65 to 5, I've lost 60. What's 0 to 500? Well, that's a run of 500. So without doing my triangle, I can just use these two numbers and see that I go down 60 and I go up 500. I go down 60 and up 500. And what I should have done here is I should have changed this, I'm sorry, to the change in Y. Change in X. Better? But I reduced this down, I divided both by 20, and I got negative 3 over 25. This is the slope of this graph.
Well, you're supposed to reduce it, right, every single time?
If you can, this is correct, but it's not precise. This is precise. Okay? Are you going to get it wrong on a test or quiz? If you probably not, I'd probably mark it right, and I would put on your test equals negative 3 over 25, just to show you that you could get it in lowest terms. Whenever you can, I would. So does everybody understand how we got the slope of this, rise over run, this change in Y over change in X? But the second question says, interpret this slope as a rate of change. Interpret this as a rate of change. Do you see the difference here? A rate of change has units to it. Do you see the difference here? Slope versus rate of change. So we're going to turn this into a rate of change, and we'll go as follows. Well, negative 3 over 25 just represents the car's fuel efficiency. That's basically what it is. And what it basically means is you lose 3 liters of gas for every 25 kilometers you drive. That makes a lot more sense. If somebody were to ask you, hey, how's the fuel efficiency of your car? And you say negative 3 over 25, they may look at you a little strange and walk away. If somebody says, hey, what's the fuel efficiency of your car? And you say, well, I'm losing 3 liters for every 25 kilometers. they can picture that. They say, okay, I drive 25 kilometers, I lose 3 liters of gas in my tank. And I'm going to talk real quickly about this again, and then we're going to move on. I'm almost done here. Now, you guys have not been in the ball game for purchasing a vehicle yet. You haven't even kind of gone to look for vehicles yet. I don't imagine most of you, at least, because you guys aren't driving. Your parents may have bought a new vehicle, whether it be new or used, but you haven't been out in that search yet. I bought a truck about 4 years ago, and one of the things that I looked for on the window, on the sticker, was the fuel efficiency. And it gives you a number out of 100 kilometers. So do you see -3 out of 25? Whenever you get a vehicle, you will see this in terms of out of 100. So this would be, I'm going to multiply both by 4. Sorry. I'm going to multiply both by 4. It'll show up again. This is going to be -12 over, can't write today, 100. I'm just going to type it in. So I'm going to go equals. If we multiply both of these by 4, I'm going to end up with -12 up top, and I'm going to end up with 100 down below. And any car dealership will always have the number out of 100. It's always going to be this way right here, out of 100. And you're looking for that top number. So my truck, this car is 12 liters. My truck was anywhere between 12 to 14. So when I'm highway cruising on 401, I just put on cruise control, I'm getting about 12 or 13 liters per 100 kilometers. But when I'm in the city, stopping, stoplight, car slows down, I got to speed up, I got to make a turn, I'm burning more gas. I'm more around 16. Okay. If you've got a nice, efficient, not a big truck like mine with a Hemi, if you've got a nice fuel efficient type car, you're probably looking at like 8 liters per 100 kilometers. You're filling up gas a lot less than what I am. Okay. I need mine for the farm. That's why I have it. But if I didn't, I wouldn't be driving around a big truck that, is going to be burning gas at this rate. But does everybody understand the difference here between slope and rate of change right here? Okay. These are the same. We know we're losing gas, so we don't have to put the negative in front, but these are the same. Slope, rate of change. Mr. Bracken, Dave. All right. So let's take a look here. Up until now, if I were to give you this, and this is what I was going to do at the start, but if I were to give you this, don't copy this out, but if I were to give you this and ask you, okay, I'm trying to get myself in shape. I went for a jog this morning. I was able to get a high-powered CBR to track my jog, and here's what I did. You guys would say this. Okay, sir, if this is your jog from your house, you went really slow at the start. Then you picked up speed pretty good. But then you slowed down again. Then you stopped. And then you turned around and went all the way home pretty quickly. I'm thinking that's what you would say. But this is just with a CBR with no numbers involved. Now that we've done these rates of change, do you see the difference with this one? I now have 5 minutes and I've got 200 meters. So let's calculate each of these, okay? Let's calculate the rise, the run, and our rise over run in our rate of change. So let's start with AB, and here's what I'm going to do. I'm going to start with A, and it's 0, 0. And I'm going to go to B, which is over 5 and up 200. So now that I've got these marked in, my rise goes from the second one. This is the second one for the rise. 0 up to 200. I've run or rose 200 meters. But my run is from 0 minutes over to 5 minutes. So what's my slope as rise over run? It's 200 over 5. We could reduce that down if we wanted to, but for right now, I'm just trying to prove the point that this is your slope. And when we go 200 divided by 5, I get 40 meters. You see on this axis, meters per minute. This is your rate of change. If somebody asks you, how fast are you going in your jog this morning? You're not going to say 200 over 5. You would say 40 meters a minute. If somebody asked you, what's the slope of this line? You wouldn't say 40 meters a minute. You'd say 200 over 5. Depending on the context, one's better than the other. Now I'm going to do one more for you, just so you understand one mistake that happens. When we go to this next point C, this is over 5, so 6, 7, 8, 9, and 10. That's 10 and up, 200, 400, 600, 800, and 1,000. That's this point. When you take a look at your rise, you're not going from 0 to 1,000, you're going from 200 to 1,000. 200 to 1,000. You're rising 800. And to go from B to C, not from A to C, from B to C, you start at a 5-minute mark and you end at a 10-minute mark. You've actually run another 5 minutes to go from B to C. So 800 over 5, which is 160 meters per minute. We knew we were going quicker here because it was steeper. We just didn't know by how much. So I did the first 2 for you. You finish the next 3. Okay, and then I'll take this up and we'll finish up. Just to finish, D is 15 and 1400, E is 20 and 1400, and F I got as 25 and 0. So to go from C over to D, 1,000 up to 1400, we rose 400. To go from 10 to 15, we're still moving across 5 minutes. 400 meters in 5 minutes is 400 over 5, which is 80 meters a minute. I love when things make sense in math, especially here. D to E, we know that we're not moving here. This is flat. But why? We go from 1,400 meters to 1,400 meters. We haven't moved. But time has gone by from 15 minutes to 20. We still went 5 minutes here, okay? So 0 over 5, and that's 0 meters a minute. Rate of change, slope. Here you could put equals 0, no problem. And lastly, from E to F. I know my run is from 20 minutes to 25 minutes. That's not the issue. But I go from 1,400 meters away from my house all the way back, so I'm 0 meters away. I've gotten back to my house. What do you have to do to 1,400 to get down to 0? You take away 1,400. It's a negative. So we get negative 1,400 meters over 5, and this is negative 280 meters per minute. Now, what does that mean in a context of your jog? You're not running backwards 280 meters per minute. You're not kind of going into the negatives in terms of the amount of space you're taking up. The negative just means the other direction. You are now going back home. This is away from your house, away from your house, away from your house. You're not moving. Now you're going back towards your house because of the negative. So if somebody asked you, how fast are you going in your last part of your jog there from E to F? You would say, oh, I was going 280 meters per minute. And they say, well, what's with the negative? Oh, it's just the other direction. I turned around and started going home. So you're getting closer. That's all. Is everybody okay with this graph, this table? Any issues there?
Yeah, I'm good.
All good? All right, here's what we're going to do. That's basically it for the teaching part of it. It's understanding the difference between slope, which is rise over run, and a rate of change, which uses the units a little bit more, and you can kind of use these points to help you out. So what you're going to do now is you're going to, and I'll have to hide this here, you are going to complete this question dealing with Misha going to the corner store and back, okay? So you have this in your book. You can calculate the speed, use your points, asking you some questions here. First part. Second part, you've got another handout dealing with what we did today. And notice a lot of these giving you the points, okay? So instead of drawing the triangles in, you see again right here where it's between lines and between lines, use the points and go and subtract them in order to come up with it. If you're having a little bit of trouble, rewatch the video or look in your notes. You can see how they're done here, okay? A little bit of a chapter problem, and then that is it, okay? After you get done, that's your homework, but please make sure you have that review to submit by 6 o'clock today. You've got another 4 hours in case you haven't done